Hi, everyone. Thank you for joining us on the first seminar in the spring semester 23. And it's my great pleasure to introduce to you Silouanos Brazitikos from University of Crete, who will tell us about the threshold for the expected measure of random polytopes. Please.
Thanks a lot for the invitation. I'm going to speak about the threshold for the expected measure of random polytopes, and it is a topic that I like very much, and I hope to advertise it properly. So the problem in general is that you want to obtain a threshold for the expected volume of a random polytope, which is defined as a convex hull of independent random points that you take with a given distribution. So the picture is like this. So you pick some points independently with the distribution, and then you make the convex hull. And the question is, and then you take the volume of this convex hull and of the polytope, and then you ask, is it big with respect to the measure or not? And how many points do I have to take in order to get the whole measure? So the first example was proven by Dyer, Fred, and McDiarmid in early 90s. So you consider the hypercube that has, of course, two to the n vertices, and it has volume 1, and then you take n points. From the cube with the uniform distribution of the cube. You make again the convex hull, say Kn, and say that Vn is the expected volume, and you ask how large you should take the number of the points in order the volume to be significantly large. And the answer is, is small. So there is a constant there, the small kappa, and you prove that if n goes to infinity, you have that this expected volume is 0 if the number of points is less than kappa minus epsilon to the power n, and it is 1 if goes to 1 if the number of points is bigger or equal than kappa plus epsilon to the n. That's why we say that there is a threshold. The threshold means that there is a point that the behavior changes from 0 to 1, from nothing to everything. And as it is stated here, we don't care about the width of the threshold, but in general we do. So here we have just an epsilon, and we'll look at kappa minus epsilon to the power n and kappa plus epsilon to the power n. So that was the first example, and then so the first question is how this constant comes up at this, and if you look at it at first time, it looks strange, and That was made clear by the work of Gatsouras and Yiannopoulos, that they generalized the work of Dyer-Freddy and McDiarmid to a general product measure. So you take n points that depend on n, on small n, on the dimension, and then you take zi again independently distributed coordinates according to a measure. Well, and here it is important that they are supported on a bounded interval. Well, if the interval is unbounded, then there was some problems in the proof. So that makes the method didn't work. So in the case that we have a bounded interval, there is also sharp threshold, and now appears where the small kappa comes. So it is the expected value of the function lambda star, where lambda star is the Kramer transform of the measure. So let me introduce the Kramer transform. So you first take the logarithmic Laplace transform of the measure, which is the logarithm of the integral e to the power c z with respect to the measure. And then the Kramer transform is the Legendre transform of lambda. So this appears a lot in the large deviation principle in Kramer's theorem, and it appears also here as the constant that appears in the threshold. So the threshold is the expected value of lambda star. Well, up to now, we saw examples that the coordinates of the points that we take independently are independent also. And let's see what happens if the coordinates of the points are not independent. The first example is the Euclidean ball. And that was proved by Dyer-Freddy and McDiarmid, then by there are some papers that they did it, and there is again a sharp threshold, but now we need previously the dependence on n was c, a constant c to the power n. Now we need roughly n to the power n half points for the threshold. So you need a super exponential number of points in order to see this this difference on the behavior of the expected value of the volume of the random polytope that is produced. And one more example is the simplex example that was done by Fries, Begden, and Scotts in 2020. And in the simplex, we need again c to the power well, D here is again the dimension. It's the previous n. So we need c to the power n points to get the threshold. In fact, here what is open in the simplex is that we know that if we take less than c to the n points, then you get then the expected value goes to 0. If you take more than, let's say, c1 to the n, then you get 1. But we don't know exactly the threshold, so we don't know which is the sharp value of the constant that we see this difference in the behavior. So it is open until now, the problem for the simplex. And let's move on to the general case now. So general, let's say, with general, I mean that you take an even log-concave probability measure and a convex body K. So the measure is supported on a convex body now, and you take again capital N points. Then, if capital N is smaller or equal than exponential to the n, then we have this estimate for the expected value of the volume of the polytope. So it goes to 0. And again, in the same work of Brazitikos and Vriciu, about the lower threshold, this now holds even if in the case that mu is an even kappa concave measure and kappa is strictly bigger than 0 and smaller than 1/n. And again, this measure is supported on the convex body K. So if you take more than exponential to 1/kappa times log n, then the expected value of the volume goes to 1. So let's see the difference with the previous results. So of course here we see that there is, so fixing a measure, there is no a sharp threshold. So we just know that if the points are smaller than e to the n and bigger, then it goes to 0. And if the number of points is bigger or equal than exponential to log n/kappa, then it goes to 1. And the other thing is that the lower threshold is for kappa strictly greater than 0. So the lower threshold doesn't contain the case where small kappa is 0, which is the log-concave case. And in fact, we did that as follows. So for the one threshold, here we don't assume that the measure is supported on a convex body. And again, if the number of the points is exponential to the n, then the expected value goes to 0. And the second theorem is again for log-concave measures. So it corresponds to k small equals 0. So then we have the following. You take a small delta, which is between 0 and 1. Then this double infimum, which is first you take the infimum overall log-concave probability measures, and then the expected value of the measure. Well, here we don't take exactly kn, but 1 plus delta times kn. Then you need exponential to, you see, n log n, which is up to the constant delta is sharp, because of the example of the ball that we previously had seen. So the problem is that do we have a similar result if we don't have this 1 plus delta there? The answer is yes, but in that case, here we miss the nice dependence here with respect to n, and we lose one more n log n, so we have n log n to squared. So there is a result for all log-concave measures, but we believe that the correct thing to have there with the dependence with respect to n should be exponential to n times log n. Okay, so now let me introduce the strategy that one should follow in order to attack such a problem. So so the first step is you make a first reduction that was introduced by the Freddie McTiernan, in fact. But as we will see, it works in general. So the first step is to reduce the problem, estimating the so-called Take half-space depth. And what is this? So you take a point x, and you look all the half spaces H over n that contain x, and you look which of them has the minimum measure. So this is then the value of this function at the point x. So this is a function that looks very geometric and nice, etc. But even in 2D, it is difficult to see what happens. What is the value for every x? And so, how is this function related to our problem? This is shown by the following lemma. So for every Borel subset A of Rn and positive t, we have that the expected value of the measure of the random polytope Kn is smaller or equal than the measure of A plus capital N, where capital N is just number greater than every number greater than the dimension, times the supremum of this function, the two keys function, when he is outside A. And so this is the first estimate that is related with the upper threshold, and the estimate which is related with the lower threshold is that the expected value of the measure of Kn is bigger or equal than the measure of A again, times this thing inside the parenthesis. So the important thing is that there you should know also the infimum of this function phi in A now. So having this lemma, we have to do two things. So first we have to choose A properly and then bound phi in that set. So again, as I said, sometimes the function fees is difficult to deal with. So the following is how we relate phi with lambda star. So some notation first. From now on, BT will be the set where lambda star is smaller than T. So the level sets of lambda star. And the first lemma that gives an upper bound of phi, and in the upper bound we have lambda star is the following. So you have a Borel probability measure on Rn, and then for every x you have that the function phi is smaller or equal than e to the minus lambda star of x. So in particular, if you remember, we would like to have the supremum of the function phi outside the set. So when you are outside BT, then phi of x is smaller or equal than e to the minus t. Okay, let's see the proof. The proof is very easy here. So we take an x, and then for any x in or n, you have the following, that phi is smaller or equal than the the measure of z such that the inner product of z with x is bigger or equal than the inner product of x with c, and then you apply Markov's inequality, and you have e to the minus inner product x with c minus lambda mu of c, and taking the infimum, then in the exp you will get the sup, since you have this minus there, and you will get exactly the lambda star of mu. So this is the proof of this easy lemma. And the hard thing is the other direction of the bound. So in order to have a lower bound on in order to bound the infimum, in fact, for phi in BT, we will get this theorem for we have this theorem only when K is a convex body. I will explain in the proof exactly the point that we don't know what to do when we have a general log-concave measure. So the theorem says that if K is a centered convex body of volume 1 in Rn, and you take the uniform measure on it, then the infimum of this 2K function in BT is bigger or equal than e to the minus t minus square root of n. So let's see the proof. So we start with a positive t, and we would like to bound this infimum of phi. And in order to do this, we take a half space 8 with whose bounding hyperplane supports BT. So it suffices to do this for the supporting hyperplanes of BT. So in that case, the measure of this half space is exactly the measure of z such that z minus x inner product with c is bigger or equal than 0 for some x in the boundary of the BT. And since we are in the boundary, c is the derivative of lambda star of x, or x is the derivative of lambda at the point x. So this happens because this is the supporting hyperplane. So then for every x we introduce a new measure, which is the tilted, the so-called tilted measure, mu c, and the density of this is the density of the measure times e to the minus lambda plus the inner product of c with z. And we do the following computation following the proof of Cramer's theorem and large deviation principle. So the measure of z minus x with xi, we write this as an integral, and then we write this integral with respect to the measure mu xi, and we also put out the e to the lambda and e to the minus x comma xi. And here in the last integral, we do integration. We do Fubini, in fact, and we bound this lambda minus the inner product of x with xi with lambda star. And the other integral is exactly the integral from 0 to infinity sigma xi, where sigma xi is the expected value with respect to this tilted measure mu xi of z minus x with xi squared, e to the minus sigma xi times t times the measure of mu xi of all z, such that this inner product is between 0 and sigma xi times t. So, and what is known here is that the barycenter of mu xi is exactly this x that it is subtracted here from z. So this is a centered thing. And as you see, the only thing that we have to do here is to bound this sigma xi. So up to now, this computation holds for all log-concave probability measures, but we can bound sigma xi only in the case of the uniform measure on a convex body. And this is because of the following. So, okay, first let's bound this thing again. We don't suppose again up to here that the measure is supported on as the uniform on a convex body K. So this is just Markov's inequality, and the other bound where the mu xi of the inner product is bigger or equal than 0 is just Grunbaum's lemma. So putting all together, we have this estimate, and as you see, the only thing that we have to bound is this sigma xi here. So, and in fact, we should bound this for all xi, so we need an upper bound for the supremum of sigma xi. So in order to do this, we will use a theorem of that was proved in the same time by Nguyen and Wang independently, and then another proof is in a paper of Fraterlesi, Madiman, and Wang that says the following: that if nu is a log-concave probability measure on Rn, and you write the density as e to the minus p, where p is a convex function, then the variance of this convex function p with respect to the measure mu is smaller or equal than n. So in our case, let's denote the uniform measure on a convex body K by mu. And in that case, the density of the measure is just the characteristic function on K. Then the density fc of mu x is proportional to a to the inner product x with z times the characteristic function of K to the point z. So now we use the fact that when you take the expected value of the inner product of xi with z, then you get exactly the barycenter of mu xi, which is nabla lambda mu of xi times xi, and this is what we called previously x, so as the inner product of x with xi. And so we use immediately the above theorem to get that sigma xi is exactly the variance of the inner product xi with z with respect to the measure mu xi. So using the above theorem for nu equals mu xi, we get exactly that this sigma xi is bounded above by n. So putting this estimate to what we had previously, we get that the measure of this bounding hyperplane of BT is bounded by e to the minus t minus square root of n, and this square root of n comes from the bound that we got of bounding sigma xi squared by n. So what we don't know, what we cannot do in the general log-concave case is to bound sigma xi like this. So in fact sigma xi is well, you cannot expect sigma xi to be bounded by n or anything, because examples, for example, for the measures having density e to the minus well, the L1 norm of x, so that there will be dependence on x, but we should find the correct dependence on x there to bound sigma xi. So to summarize here the theorem, if we set omega to be the logarithm of 1 over phi, then we have the following estimates. So up to this square root of n that doesn't play a role in the story afterwards, lambda star is the same with omega, so it's the same with the logarithm of 1 over phi for every x in the interior of K. And moreover, this is a Cramer theorem for the uniform measure on a convex body. So let me summarize again the strategy. So we reduced the problem in the beginning to find bounds for this function phi. And here, using this this corollary, it suffices to have bounds for lambda star. So, in order to solve the initial problem for any uniform measure on a convex body K, this is equivalent to find thresholds for the volume of the sets BT, the level sets of, namely the level sets of lambda star. So let's see how we can find such thresholds for BTs. So let m, small m, to be the expected value of the lambda star. So this is going to be the desired threshold, and this is our big conjecture that for every convex body K, the threshold will be exactly the expected value of lambda star. So the first thing is, suppose that m is finite. Well, it is not trivial that m is finite. I will comment on this afterwards. But since lambda star is infinity on the boundary of K, it's not clear that this expected value is finite. So then we use Chebyshev inequality to get that the measure of lambda star smaller or equal than m minus an epsilon, which is on 0, 1 and 0, 1 times m, is smaller or equal than the expected value of lambda star minus m squared over epsilon squared times m squared. And this veta of mu is exactly this thing here. So the variance of lambda star over the expected value squared. And we have bound also from the other side. So lambda star is bigger or equal than m plus epsilon times m. The measure of the set is bounded above by the same veta, the same parameter veta over epsilon squared. So using this simple argument, we get the following: that if we knew that this parameter veta goes to 0 as n goes to infinity, then the threshold for the BTs will be the expected value of lambda star. And the same happens, of course, then going back that will be the threshold for our problem of the expected volume of the volume of the random polytope. So here there are two open problems until now. To prove that small m is finite, and then to prove that the veta is going to 0. So we were able to solve only the first problem. So the theorem is that, in fact, so suppose that K is a center-convex body, and in general, take a measure which is kappa concave, and it is supported on K. In particular, you can take the you can produce from there the uniform measure on K, so it is contained here. Then the expected value of lambda star is bounded by log n over kappa times the infinite norm of the density. So this means that in the case of the uniform measure, you will get that the expected value of lambda star is bounded by n times log n, which is exactly what you get from the Euclidean ball. So the only open problem in the case of the convex bodies is to prove that this parameter veta goes to 0 as and goes to infinity. In the log-concave case, even this problem is difficult. So we were able to prove just the following thing. So take a centered log-concave probability measure on Rn, and so the assumption here is the following. So you take a function that goes to infinity faster than the logarithm. And you suppose that, so this is an assumption about the centroid bodies of mu. So this says that the centroid bodies are increasing in a sense. Then the lambda star has finite moments for every p bigger or equal than 1. But in the general case, if we don't make such an assumption, we don't know if it is true or not. I mean that the expected value of lambda star is finite or not. And finally, let's see one application that was known, but with our method we did the threshold sharper in the case of the Euclidean ball and in the case of the cube. I just mentioned the what we got for the Euclidean ball. So then, if Dn is the centered Euclidean ball of volume 1, then we there is a sharp threshold of the initial problem with parameter small kappa equals to the expected value of the lambda star of the ball, which is n+1/2 times the harmonic think of n½ plus something which is big O of square root of n. And of course, this harmonic thing is like log n, and this is why in the ball you take n times log n. Thanks a lot.
Thank you very much, Silouanos, for this very interesting talk. Are there any questions? So maybe I'll ask a question in the meantime. So you were mentioning when reducing to the half space depth that there is a certain good choice of the body in there, because the proposition said that for any set A, you can have this inequality.
Well, you choose yes, you choose A to be the BTs in our case.
You do choose them. Okay,
So
thank you.
You choose A to be this BTs.
And do you know whether that's an optimal choice?
Well, no. You can make a lot of choices there, but we did this because in these sets you can bound both you can bound lambda stars, so you can bound phi.
Sure. So do you have a suspicion where this extra n log n comes from, in which place you're losing?
You mean this? So here now I described the general strategy of finding the threshold, which is something else from this thing. So this thing was made in another paper, but I just mentioned because it is also open to see what is the optimal number of points that you should take.
Thank you. Are there any other questions? Okay, if not, thank you again, Silouanos, and well, see you soon, I hope.
Thank you very much.
Bye.